There we go. Cool. Yeah, thanks for having me. My name is Bobby. I guess let's start with a little bit of background so I know what everyone knows. Who here knows what differential privacy is and how it's used? Okay, great, because most of the talk is getting you up to speed on that. The big goal is to take data sets that are private, so think healthcare, finance, maybe government type data sets, and be able to do AI on them and let the world use that AI. So the dream is we can take all the cancer data from the American VA, from European hospitals. We could train machine learning models to predict diagnoses or predict what treatments will cure people. And then we could take that AI trained on tons of data and give it to all the doctors in the world. And the problem with that is there's serious privacy concerns with the data sets, and we're trying to get around that. So that's what we're going to talk about. Here's my introduction slide. That's me on the first day of grad school. I woke up late. I was really into tie-dye, and I made that shirt, and it was picture day, and I didn't know it. So that for 7 years sat in the graduate department. And this is a little bit of my background here. I spent 5 years teaching math at Purdue University while I was getting my PhD in math, and that was a really great opportunity. And then I decided to go into much more applied research, and I landed at Oak Ridge, and I've been there since 2012. I got hired as a postdoc to do anomaly detection, so it was probability theorems, stuff like that, and it got defunded like 2 months after I got there. So I ended up doing a postdoc on natural language processing. And for those of you in that field, this was like before Word2Vec. So the field has changed a lot since then, and I wouldn't say that I'm still, up to speed on the modern algorithms. I got promoted to staff, and this is just to show you a little bit of all the different types of things that I've worked on and kind of how it is at a national lab for those of you who are grad students thinking about different careers. But you work on all kinds of different stuff, which is great. You become a master of none, but you become really broad and you can cross-pollinate ideas. So, things from graph theory to using machine learning to predict how much power GPU systems are going to use. I worked in a team that did back end to front end. So we had front end folks that built really nice UIs, and then I helped with algorithms, and we had back end people. We actually developed an anomaly detection system that's used in cyber operations at the national lab. So they have their network flow logs, their high volume logs of data on basically what computers are talking to which other computers. And we have an online algorithm that models the statistics of how every computer on the network interacts. And when those start to go bad, they alert the operators. And like I said, the front end guys put a really nice front end and it's in use. So that's pretty neat. I was the lead for a couple of years on our vehicle security project. So we were trying to understand the network inside a car. There's lots of little computers in your car that talk with the controller area network. And we were trying to do anomaly detection there. And what we actually ended up coming up with was a way to reverse engineer obfuscated messages. So when Volvo or Ford or Toyota has the little computers in their car talk to each other, the way they encode the messages into bits is proprietary. Every company does it different and they don't tell anyone. So if you go look at control area network data off your car, which a lot of cars you can plug right into the OBD2 port like a mechanic and just get the data and see the bits, you have no idea what they mean. And so at least we had the state-of-the-art technology to reverse engineer that. So we built a pipeline, machine learning pipeline to reverse engineer that. It turns all the bits into signals. And then the hope is you can now detect attacks by doing time series analysis because you have signals of the sensors in the car. As he mentioned, I was a manager for 2 years. And here we set up a big test bed, so a data center, and we would emulate users. So we had a machine learning tool to have fake users log in, send each other emails, et cetera. We instantiated them on VMs, and we made those VMs have software that's got known vulnerabilities. And then we would instantiate commercial cybersecurity tools to test them. So we had commercial partners that would give us malware detectors, network detectors, et cetera. We'd put them on there. We actually had a 10 gigabit line from the actual lab's network, so we could stress test them in terms of how much bandwidth they could take. So we had real data going through them. And then we ran these big experiments to see which cybersecurity tools work and which ones don't. The long and short of that, and there's a couple publications on it, is they don't work as well as the salesmen say, and it's pretty scary. So I'm going to talk to you about what I do now, which is AI and private data sets. But before I do that, I guess I'll tell you the one other project I'm currently working on. So for those of you who've had differential equations, there's a lot of systems that you can model with ordinary differential equations. And the thing that makes systems work is feedback. This is where control theory comes in. And you can think of your human body as an example. So if you don't have the nutrients you need, somehow your brain tells your body that you're hungry, then you eat, then you get it. If you eat too much, right, it tells you you're full and you stop. And you can maintain homeostasis because of the feedback loop. If you think about critical infrastructure, dams, for example, have a control system. We know how far open or closed the dam is. They have to manage the reservoirs. So downstream, the farms have the water they need throughout a whole long summer, for example, in a deserty area, so that we can make the food for the people to eat. You also need to continuously run water to meet power generation needs. So we have the electricity we need. And so there's sensors throughout the river. There's computer systems that do this feedback loop. So this is how we keep things in control. The downside is, in almost every system, you can mathematically prove that small perturbations to that feedback loop can lead to complete destabilization. And the easy one to think about is, imagine if your brain just told you were a little bit more hungry than you needed to be. Over time, your homeostasis would go completely out of whack. And so what we've got is a math pipeline, basically, where we can find minimal perturbations to systems that will completely destabilize them. And so we're using this to find vulnerabilities in systems. That's kind of the next step, is apply it to high fidelity models of systems to learn those vulnerabilities. So that's just a quick overview of kind of like what I do, what I've thought about. And now we'll get into the meat. Since there's, maybe we won't get into the meat. I forgot I put this in there. Since there's a lot of graduate students, I always include these slides. Internships at Department of Energy National Labs in the US are a really awesome opportunity. And there are tons of different programs. I only listed a few here, but this website here, and I can give you guys the slides. If you want to see all the different awesome opportunities, I'd encourage you to think about applying there. And whenever I talk to grad students, I think this is advice that I always like to give, because I think it's more important than the science you're going to hear from me today. Whatever you decide to do it with passion. If you're doing something you don't love, you're going to do a poor job and you're not going to like your life. If you do something that you love, you're going to do an awesome job and your life's going to be awesome. It doesn't mean work's going to be fun every day, but I think that's my one big message. I'll leave the other ones off there. Last thing before we get into the meat, this talk's for all of you. It's not for me. I don't care whether I get through all my slides. I want you guys to learn something. I want you to take away something. So raise your hand, interact. And we'll make amends as we go to get through whatever we feel like we need to get through. So for those of you that want to learn these topics, this is how I learned them. So I can give you these slides. If you want to learn differential privacy, there's the formula, because it's kind of an esoteric math topic, and I can give you references that'll get you through the epsilons and the deltas. We're going to talk about normalizing flows, which is a class of deep learning models. They're not that hard to learn. And then the paper that I'm talking about is currently submitted to privacy enhancing technologies. And we have a pre-draft there. We'll have a better draft next week go up online. Okay, so I kind of mentioned the motivation. Has anybody here ever checked out this website called Papers with Code? Yeah? So it's really interesting, because the way the website's designed is they take a whole bunch of different problems. Like, we want to, be able to tell whether a cat's or a dog from image processing, or we want to be able to translate language and text from one language to another. And there's tons of these different types of problems on that website. And if you click on one, it gives you every benchmark data set that's been released. And if you click on the data set, it shows every paper that's been published with their code and how good their accuracy is. And the thing that is remarkable about this website is you can randomly select them. And I didn't this morning have time to get it going. I would have done it. But you can just randomly select, pick any of them that you want. It doesn't matter what it is. And in a 10-year time frame, machine learning almost always solves the problem. And the example is ImageNet. So Feifei Lang, instead of working on image processing as a young professor, said, if we just have tons of data, we'll solve this problem. And she used her research money to hire people through Autoturk to label images. She made this enormous corpus, millions of images. And in 10 years, the accuracy went from something like, did I write it up there? Yeah, 75% to 95%. And so the point is, there's a lot of problems in the world that if we can just get good data sets to you all and us, the AI and software engineer type researchers, will solve the problem. And this is a great example. This is from 1 year ago in the New York Times. Image processing can detect breast cancer better than humans. They've already deployed this in Hungary to assist doctors in finding breast cancer. So this is like a huge success story. Like, this is why, in my opinion, we're all here, right? Make the world better. And now we get to the problem. There's a whole bunch of places where we really, really need AI to help. But the data is so private, we can't release it to us, the researchers, to use. We are the adversary, right? We can't know everyone's healthcare data. So the first idea was, let's just anonymize the data. And you can't do it. Like, that's basically what they find. And I'm going to tell you a couple of examples. So in 2017, Australia, who has nationalized healthcare, took all their healthcare records of their citizens and they anonymized them. So they scrubbed out the names, they took all the dates and they aggregated them to the month. They scrambled the provider IDs, which is like the numbers that identify the doctors, and they put them out there. So machine learning researchers could learn, predict treatment, predict diagnoses, et cetera. Very quickly, a privacy researcher identified herself in the data set and gave the formula to identify what she said was 17% of the women in the country. And here's how it works. And I've actually done this talk when I have more time, where I bring up a fake data set and I have you all tell me what queries to write. And I see if you can identify me in the data set. And just from what you know about me right now, you can do it. And this is how it works. I'm male, filter by male, half the data set's gone. You can roughly guess my age, right? I'm around 40. Filter between, 37 and 43, maybe a tenth of the data set is left. So a tenth and a half, now you're down to 1/20th. I live in Tennessee near Oak Ridge National Laboratory, right? Go look up the zip codes. Filter by all those zip codes. Now you're down to, 1 in 100th. If you just know, say, 6 facts that are 1 in 10 facts, like say you knew my birthday was in January, that's 1 in 12 roughly, right? If you know 6 of those, what's the probability of someone satisfying all 6? It's 1/10 to the 6. You just identified me out of 1 million people. And so Cynthia Dwork, who's kind of the matriarch of this field, said, de-identified data isn't the culprit's auxiliary information. Netflix released statistics on how people rate movies. The movies you've seen clearly identifies you very easily. Nobody's seen the combination of movies. You overlay that with IMDb, which is public, you could identify everyone. They got sued and lost. And so let's go to our problem. We've got private data. We don't actually want to anonymize the data set. We just want the machine learning model that'll predict cancer or fight crime or identify fraud to be released. We just need to train it on this data. And then the important complicated statistics that happens to do whatever inference we want is encoded here. Why can't we just do that? And the reason why is this whole field of like offensive AI security called membership inference attacks. If someone hands you a trained model, you can run attacks just on this model to figure out what was in that training data set. And you guys might have seen some of the recent papers where they've done this with LLMs, where they feed it a bunch of garbage text, and like ChatGPT-4 will spit out someone's name, address, phone number, et cetera. We'll talk at the end of this talk about how you run those attacks. But the point I want to make here is that if you just train a data on private data set and you release it, you're leaking people's information, potentially. We can't do that. And so this is the big conundrum. Like, how do we pull this off for all these private data sets? So here's your background on differential privacy. And if you need to know it without knowing any math, it's just lying randomly. If I lie randomly, then anything I say, you don't actually know whether it's true. But if I do that randomness smartly, you can still do whatever statistics you need and figure it out. Figure out a good enough answer to be useful in the real world. So let me give you the concept here. Differential privacy is really a math definition. I'm going to show you that on the next slide because it's hard to understand. I'm going to try to give you the intuition. So feel free to ask questions. So let's orient ourselves. This is broader than machine learning. It actually came out of database queries. Like, I just need to know the average age of the voters in my district from the Census Bureau, say, something like that, right? But you can use it for machine learning too. So we have a data set, it's private. This is whatever we want, some function on it, right? Tell me the average, tell me the count, train a machine learning model. I want to release something. What we're going to do is we're going to inject noise. So this deterministic algorithm now becomes a randomized algorithm. The easiest way to do this is not how we always do it, but the easiest way is compute the real answer. You would compute this in the private data enclave, right? And then sample some random noise that's centered at 0 and add them together. So if I didn't want you to know my real age and I was using this, I would say, oh, I'm 41. But then I would go sample from like a Gaussian distribution centered at 0, and I'd get, I don't know, -1.2. And I'd say, actually, I'm, whatever the math is, 38.8 or whatever that comes out to be. Why do we do this? So I want you to imagine this is the private data set with your data in it. And this is a private data set where they changed one data point. And the one data point they changed was your data. They took your data out. They overwrote it. They changed your age. They changed where you live, whatever. Okay. When you run this randomized algorithm on the real data set, you get a probability density, right? Because it's a randomized algorithm. So you're getting a sample from a probability density. It's going to be a sample from, and this is a Laplacian distribution. I'm going to tell you why I drew that one, but you could draw a normal, draw whatever density you want. If you change the data point, you change that one data point, you take your data out, you get a different density, right? If those two lie right on top of each other, it means it's impossible to tell whether that one data point was in there or not. You could have the whole densities, not just one sample, and you couldn't tell. If those two densities are really far apart and you have one sample from them, you could tell that that one data point was in there or not. So the idea is if you take, and this is where the power comes from, any two data sets that differ by one data point, not just the real one, right? Any two data sets that differ by any one data point, and you can prove that these are very close to being on top of each other, then it's impossible to tell any one person's data from those data sets. Does that make sense? So we're going to measure the distance, the maximum distance between these two. So it would be here, and here would be the maximum distance across all pairs. So take the supremum over all of those. That's a positive number, so you can write it as e to the epsilon. Epsilon is your privacy parameter. So that's what the definition says. If this density, when you have data set X, divided by this density, when you have data set X prime, so I guess it's not the difference, it's the ratio, but you get the idea. If that's always less than e to the epsilon, then you have epsilon privacy. The thing you need to know here is if epsilon is really small, those two are always on top of each other, which means you can't distinguish on one person. That's really strong privacy. If epsilon's really far apart, that means that there's at least one pair of data sets and at least one person that you could probably distinguish. And so that's really bad privacy. If you read the literature, they also have this definition of weak or approximate differential privacy. So move the denominator over so it lands here and then add a delta. The way you should think about this is delta is a very small number. With probability 1 minus delta, which is what's probably going to happen, you satisfy the good definition. But there's this tiny probability where it doesn't happen. So you should be leery of that and make sure it's not catastrophic failure. So catastrophic failure is with probability delta, you like publish the whole data set. That would be really bad, right? We wouldn't use that. And in real life, usually there's a trade-off. So there's a continuous curve of trading epsilons for deltas. So this is just differential privacy. It's just a math definition. And this gives us the foundation to now build algorithms, whether they're simple statistics, like how do we compute means and how do we compute counts from data sets, to training full, big neural network machine learning models and mathematically guaranteeing privacy. The fact that this is useful for actually doing the algorithms is why it caught on. And I should mention that won the 2017 Gödel Prize. It's kind of the worldwide accepted standard for privacy. The United States Census in 2020 required differential privacy on what they did. It's used by Apple, it's used by Google, it's used by Amazon, according to what they say. So this is kind of the standard the world is accepting. We'll do one quick example here. So your mom comes home and the cookies are gone. She thinks you ate all the cookies. And so she asks you, were you in the kitchen last night when all the cookies were murdered? So I'm going to give you two algorithms because you don't want her to know the truth, right? The first algorithm is you flip a coin. It may not be fair. It may be a 70-30 coin, but whatever. You flip a coin. If it's heads, you tell the truth. Oh, sorry. If it's heads, you lie. If it's tails, you tell the truth. So I'm going to ask you in a minute if this gives you differential privacy or not. Here's the second one. If the answer is no, you have nothing to hide. So you're just like, no, I wasn't here. I was out with, my friends. If the answer is yes, you have something to hide. So you flip a coin. And then same algorithm. If it's heads, you lie. If it's tails, you respond honestly. So here's the rule of thumb you should think about with differential privacy. Whatever algorithm you use, does it give you plausible deniability? So this one here, do you have plausible deniability? Whatever you answer, could it have been the other thing? Yeah, so this should satisfy the math definition. How about this one? So this one's trickier, and here's why it doesn't work. If you answer no, it could be that you answered truthfully and you never flipped a coin. And it could be that you lied and you flipped a coin and you got heads. If you answer yes, could the real answer have been no? No, there's no plausible deniability for yes. That's publishing the data set. So this gives you differential privacy, this one doesn't, and I can tell you how to compute the epsilon. If you said there's some probability that I was not home and the answer is no, and there's some probability I was, that probability would be the delta, because there's some probability you're going to just publish the data set, and there's some probability you're going to actually do the algorithm that gives you epsilon differential privacy. So that's kind of the like rough idea. The reason this is important is when you prove theorems, you can take really hard, complicated differential privacy mechanisms, and if you know they satisfy epsilon differential privacy, you can make them basically mathematically equivalent to this, and this is easy to analyze mathematically. Same thing for this. If you're epsilon delta, you can basically get it to look like something like that. And this is just to show you how the math works out. So the real data set is 0 or 1 for yes or no. And if you actually say, well, what's the probability I'd say yes? If you write the coin in this form, which you can always write a number between 0 and 1 in this form, that's how you get the epsilon. So you can see the biggest one, biggest one is epsilon. Here, what goes wrong is what we discussed. If the real answer was yes, there's no chance that you could say no. So you get a 0 in the denominator of that math definition, and then your epsilon has to be infinity. So that's really weak privacy. So that's the idea. The reason I drew these tent-like distributions is that's the easiest way to prove differential privacy. So let's say you want to know how many people in the data set, I don't know, have cancer, something like that. So g of x is just a count. What we're going to do is we're going to sample from a tent that's centered around 0. And the density is just e to the negative absolute value of x. If you're not used to Gaussian distributions, normal distributions, it's e to the x squared, right? And the reason we just do an x is because it makes the definition of differential privacy just fall out. So pretend your data set x and your data set x prime are any two data sets that differ by 1 point. Divide these densities, right? You're going to get e to the absolute value of g when you plug in x and g when you plug in x prime. And then this beta term controls your variance. So you want that to be less than epsilon. So you just solve for beta and say, well, how do we solve that? And this is the really important part. In order for this to be less than epsilon, you have to know how big your algorithm, the deterministic one, could be when you have one data set versus any other data set that differs by 1 point. That's called sensitivity. If you change 1 point, how sensitive is the output? That's what drives the definition. So you have to be able to compute this, and that's hard in real life. Let's go back to my example. We're doing count queries. So if you change it, like, count how many people have cancer in this data set, change 1 row, right? You change 1 data point. Your count could be the same. It could go up by 1 or it could be down by 1. So those can only differ by 1. So in this case, S would be 1. If you want to do something like, what's the average income of, I don't know, my city? Now things could get really tough. Because if Elon Musk moves to your city, that's the 1 data point that changes. Your average is not a robust statistic. It could be wildly different. And that S is going to be enormous. What that's going to force is you're going to have like infinite variance here. So you can get really good privacy, but you're going to just throw out complete random numbers. There's going to be no utility. And this is the problem with differential privacy. There's a lot of problems where it works well for. There's a lot of problems where the trade-off between good accuracy and good privacy is untenable. You can't use it in real life. One last thing. If instead of adding the weird Laplacian noise because it makes the proof, like a one-liner, you want to add Gaussian noise because we all use normal distributions because of, I don't know, central limit theorem and bell curves and stuff like that. You can do it. And the amazing fact is that you cannot get, you mathematically cannot get epsilon differential privacy out of it. You always have a positive delta. And the good news is there's a continuous trade-off between the epsilon and the delta. There's no catastrophic failure. There's no chance where you're going to say something and then they know that has to be true. So it's not as bad as it seems. So this is used in practice. So let me tell you what I'm driving at with this like crash course in differential privacy. Just a sec. I just want everyone here to know how you do differential privacy with AI, because that's where my research starts. But I think this is going to be really worthwhile. Yeah.
So this definition of R2 is it implies that the attacker has all the data except for one.
No, it assumes that the attacker doesn't have any data. It assumes that they know the algorithm you're going to do to add randomness. When your mom asks you whether you were there last night and ate all the cookies, she knows whether you're going to flip a coin and then lie, or she knows if it's no, you're just going to tell the truth, and if it's yes, you're going to flip a coin.
Because it feels to me, this definition, it feels like it's very strict. Like you comparing this, how realistic is it in a real case?
They use it. It works. That's why it's adopted.
Yeah.
Yeah. So I'm told, I don't know much about, what's the term? I guess the term's AI security. You know, there's folks who do adversarial machine learning is the term I'm looking for. Like, think about this for adversarial machine learning. Why does do you guys know what adversarial machine learning is? You have a picture of a cat, you change one pixel, a human couldn't even tell you which pixel changes, and the algorithm that, you know, gets 100% accuracy on predicting cats versus dog thinks it's a dog. And you're like, how, right? What's going on there? I mean, just think back to the definition of continuity from your Calc 1 class. If this is all the images, the floor is the feature space for the images, and I'm standing on the cat picture, you take like 1 pixel movement, which is like you step this much, and you just fell off a cliff, right? It jumps all the way to dogs. It means you're hiking on a trail, and there is, in one direction, there's a cliff you could fall off. So you could imagine a definition where you would say, we're only going to use algorithms that the loss function is very continuous, like it satisfies a Lipschitz condition, and then you could guarantee there's no cliffs. So I'm told, I'm not in that field, that people have tried to make those definitions, but they don't work. You can't train machine learning algorithms that satisfy them and have accuracy. So all of those algorithms have cliffs, I'm told. Again, I'm not in that field. The thing about this is it works. You can create mechanisms to do basic statistics as well as train modern machine learning algorithms that satisfy this definition, and they get decent accuracy. So I don't know if that helps.
Yeah, kind of. But to me, it sounds like the definition is very, very strict. Like you just have one data point that we would kind of remove from the. Are there ways to kind of?
Oh yeah.
The definition?
Absolutely. So I would say there's one way to harden it, which is group differential privacy. So like instead of saying we're going to look at any two data sets that differ by 1 point, we're going to say they differ by k points, like k people. There's another one that I guess it's called local differential privacy, and I'm a bit over my skis because I read this at one point. You can correct me if I get this wrong, but
I mean, there is a paper on differential privacy, and they have 200 different movements.
yeah, there's a lot of notions, and I haven't learned all the other ones. But the group privacy is one, and I think is local differential privacy where you only care about your data sets and the data sets that are one away from yours. So it's much weaker. Yeah. So yeah, I think there's a history of definitions, and none of them caught on because I think my guess is this one's actually much more useful. Yeah. Yeah.
Yeah, so I'm thinking about this essentially your question.
Yeah.
For the function G, I assume. Like, could you have a data set that satisfies the differential privacy for one question, but not for another?
Yeah.
Like,
Absolutely. So the count query is a good example.
yeah.
So take the Census Bureau, you want to count how many people make over $100,000 a year. The sensitivity is 1. So you can just use the Laplacian mechanism and you can get really good privacy with pretty good accuracy. Then you say, I'm using America as an example. I want to not count how many people are over $100,000. I want to know the average income. The fact that like people like Elon Musk make, I don't know what he makes, $7 billion a year, they're going to make it so if you want the same privacy, you have to use an enormous amount of variance. So you're going to be sampling numbers that could be negative, literally, because the variance is so wide, which doesn't even make sense. So yeah, there's some problems this is well suited for and others it's not.
So you could like have like take one question, you forgot one question, then you release it, and then you can get, you could get some information from the data set, even if you had ensured they couldn't for a bunch of other questions, you could forget one.
Yeah, absolutely. And we're going to talk about it in a minute, but intuitively, every time you ask a question, you answer a question with, say, epsilon differential privacy, If you answer another one, your privacy on the whole data set should go down. Right? So I'm going to show you the math of how we deal with that. Yeah.
So you were talking about census data. I love talking about census data.
Okay, cool.
And so one thing that I'm wondering about is something like this. So you know that in the census, right, with ethnicity, that's a really big problem in rural areas, because if you have a small zip code, it's potential that you have just like one person that belongs to a certain ethnic group. So how does this approach granularity?
So if you said, I want to count how many people are of a minority demographic in an area that doesn't have a large population.
Without identifying that individual, if there's only one person that
Right.
identifies it, without like excluding them from like accurate results.
So the question is, how good is the accuracy? So if you said, I want to count, and the real answer is 1. So if you use this, you put a Laplacian distribution over 1, and then you sample from it. So you might get -3. You might get 4, you might get 0. I mean, and then if you want that to be a more narrow distribution so that it gives you a number very close to 1, well, then your privacy is going to go out the window. Basically, the larger the variance, the better privacy. I don't have a good rule of thumb for like how you balance those. The rule of thumb is epsilon should be between like 1 and 10 is bad. 1 is good. If you shoot for around 1, you might end up with 2. That's okay. That's like, and then the rule of thumb for delta is 1 over greater than something bigger than n, where n is the number of people in your data set. And I don't remember the intuition, but it's like very low probability that that epsilon won't be satisfied. But again, in practice, if you move your delta bigger, then your epsilon gets better. And if you move your delta worse, then your epsilon, whatever, there's a trade-off. If your delta is worse, your epsilon's better, and vice versa. So it's not a strict jump off, really. It's a curve. Yeah. Yeah, we're good? Okay, thanks. So there's a couple of things you need to know. If I give you something with epsilon privacy, I give you out an f of x, you go and do whatever you want with it. You run it through a machine learning algorithm, you do computations with it, same epsilon holds forever. You can post-process all you want. It's only that initial release from the data set that works. And if you just write down the definition of differential privacy, the thing you want to compute where you did some other algorithm on top of the thing that was released, you get that, which is the same thing. So easy to prove. You don't have to worry about post-processing. To the question about if you're releasing multiple things, your privacy should go down. The easiest thing to prove was proved way back when they invented the field in 2006. If you ask me a question, I release something with epsilon differential privacy, then you ask the second question, I release it with epsilon differential privacy, and we do that k times, then it's very easy to prove that your overall privacy is k times epsilon. And if you have deltas, it's also k times delta. That grows linearly, that's not great. You can basically do tail bounding if you're in that kind of analysis to prove a more advanced thing. So this, if you have k queries, is how the epsilon grows, this nasty formula. And this is how the delta grows. This is k times epsilon. This guy looks like square root of k times epsilon, which is a smaller number as k gets big. And then for small k, you get an epsilon squared in front of it. So it's better. So I plotted those two. So if you had 20 queries, these two would be the same for this epsilon. If you were doing a small amount, you'd use the linear bound. Both of these hold. The point is they're not tight. Right? They're both true. So this would be what you'd use, and then you would use this. And you can see it's linear asymptotically, but with a better slope. And what I'm here to tell you is there's 15 years of research trying to figure out if we're releasing information over and over, how tight can we bound this? And just look at the progression here. So these are the two that I showed you. I guess that was 2006, sorry. Took 4 years to get to that one. These guys proved it. They got tight. They know exactly what it is. That's the best you can get. And then these guys proved that it's sharp P. That's worse than NP complete. So we know the answer, but we can't compute what it is, which is kind of funny. The math gods aren't always nice. These ones approximate it, and this is the state of the art. I don't know how it works, frankly. I've used it. I haven't learned the math yet. But my point, what I want to lead you to is that there is a lot of work trying to make this really useful. And I think we might want to rethink how we're doing things. And that's what my project's about. Okay, we're to the point where on the next slide, you're going to know how to do machine learning with differential privacy. But I have to make sure people know how machine learning works. So I guess don't be embarrassed, but like Does everyone know how to train a machine learning model? Should I go over it?
Sure.
Okay, good. Thanks for speaking up. We're going to start with linear regression because most people have had that either in a calc class or a linear algebra class or a statistics class. The way I think about machine learning, supervised machine learning, is someone gives you an input x, there's a function you don't know, f of x, and you want to guess what f of x is, and you get to start with a whole bunch of inputs, x's, and a whole bunch of outputs, y's, and then you have to guess what that function is, right? That's what it is. It's like name that tune. So I'm going to do linear regression because that's what corresponds to the easy example. And so if you did linear regression, the x would be multiplied by some constant that you don't know, plus another constant. Those are the b's. So we just have to figure out what b's are the best. So what you do is you plot all these points. The black points are the data that you're given. Draw an arbitrary line. So we would know what the b1 and the b2 is for any line, right? So, and then measure the red distances. And then I'm going to sum all those up and square them. So this is the real y's. That f is my guess with the two b's that drew the blue line. This is the red line distance. Square that, add that all up. If this number is small, then that line is a really good fit. If this number is big, it's a terrible fit. So what we're going to do, think of this as a function of b1 and b0. That's called your loss. And then we're going to just optimize that. We're going to minimize that. We're going to find the b1 and b0 that makes this as small as possible, and that'll give you the best fit line. When you go to neural networks or deep learning, et cetera, you're generally of this form. Your x is a vector. Your a is a matrix. So you multiply, you get a different vector out, and then you apply a nonlinear function to each component. All of the a's here are constants like the b's, and there might be also parameters in that nonlinear function that you want to learn. And then you do that over and over and over again. So you just write that down, and then here, instead of it being a straight line, it'll be wildly curvy. It's very expressive. And then you do the exact same thing. You create a loss function, and then you solve for all the constants in the a's and the b's by minimizing that. That's how it works. So how do you actually do this optimization? If you're in Calc 1, you set the derivative equal to 0, you get all those roots, then you go check to see which one's a minimum, and that's it. We can't actually solve setting the derivative equal to 0 in this like real world setting. So you have to use like a iterative algorithm. So here's the way it works. If you remember from probably the second calc class, if you take the derivative in b1 and b0, so here, this is all the b1s and b0s on the floor, and this is the random guess. That's the blue line I started with. If I take the derivative, it's called the gradient, and it always points in the direction that is uphill for that function. But I don't want to go uphill, I want to go downhill. So I'm going to go in the opposite direction, and I'm going to take a step. And then I compute the derivative again, that point's uphill, but I don't want to go uphill, I want to go downhill, and I take a step. And you just do that over and over again with some randomness so you don't get stuck in a local minimum. That's how it works. Okay, so that's how machine learning works. Let's do it with privacy. This is the state of the art. This is what people use. When I compute that gradient, this tells me which direction is uphill. I'm going to turn around, and instead of stepping downhill, which is like the smart person walking home, pretend I'm drunk. I'm going to add random noise, Gaussian noise, to my direction, so I'm going to miss a little left or right, and I'm going to make sure I don't take big steps. Remember that sensitivity that we had to compute to do anything if it was how much your algorithm's output could change when you had any two data sets that differ by 1 point, and we had to bound that because it tells you how much variance to add. That's why you clip, because that gives you that for free. You get to know that for free. We're just like, if it's a big step, we're not going to take a big step, and now I know that the sensitivity is not too big. The reason you do this is that every single step, of which it takes often thousands, tens of thousands, you get a privacy guarantee. You can release which direction to step. That's what you're releasing with this from the private data set. So someone says, I want this machine learning algorithm trained with privacy. You don't give them the algorithm, you give them every single step, and then they start at the same point and they walk all those steps and they'll end up with the right algorithm. How do you know the overall privacy guarantee? Every single step we released had an epsilon and a delta. The reason there's a delta that's positive is because we use the Gaussian noise. So you have to go back to this last slide with 15 years of composition theorems and pick your favorite one. Apply the one that you think's best. It's not great. It's like super wasteful, right? Like they just want the algorithm. You gave them 10,000 drunk person steps to try to find his way home. Every single one costs them privacy. The overall privacy guarantee gets worse with every single step. Like it's a horribly wasteful design, in my opinion. And you always have delta bigger than zero, which, you know, it's not the worst thing, but like, it's not great. So my thought was, I want to overthrow the king. Like this is what everyone uses. If you go use PyTorch, you can just download a professional package from Meta and it works awesome and you can implement this. And you can choose different composition theorems here. It's really cool. You can do it with TensorFlow, but I've never done it. So this is like in production. And I want to overthrow this king with something that's much more efficient and hopefully pushes the accuracy and the privacy. So you get better accuracy and privacy. Let me show you some results. This is from a blog. This isn't like a published paper, so I don't think they did a lot of optimization, but I think it proves my point. Remember this whole like, we need really good data sets, and if you put them out in the world will solve it, and that was ImageNet. This is the ImageNet data set. It's that data set. ResNet is the model they use, so this is a deep learning model. If you go just run that model with some reasonable hyperparameters, you'll get 70% in their accuracy metric. If you go run it with differential privacy, this is your epsilon. So big epsilon is bad privacy, low epsilon is good privacy. Remember, 1 is good, 10 is really bad. You usually end up like around 1 or 2. If you're at 2, you are at 15%. It's like not even useful. So we got to take this whole curve and we got to shift it up and left to make this useful. And there's some problems where this works pretty well, back to the question, and there's some where it doesn't. Here's an example. So this is electronic healthcare record data from people in the ICU at a hospital in Boston. They've somehow been able to make this public, and you have to go through some IRB stuff to get it, but it's a public data set. This is basically predicting whether you're going to die if you make it into the ICU based on your first day's data. If you do no privacy and you just train logistic regression, which is like the easiest machine learning model in the world, not very expressive, you get 82%. If you add differential privacy with an epsilon between basically 1 and 3.5, you drop 22%. It's not great. The problem here versus this one, so this is a really sophisticated deep learning model. It's a recurrent neural network that's made to deal with missing data. It's really smart. You'll drop 6% from the state of the art. So why are those really different? The conjecture is that the data distribution has really wide tails. So back to your question, like, what if I live in the tail of my distribution? I'm in a demographic that is not well represented. That really affects how good the model can be. And it also means that you may not have as good a privacy. So there's an algorithmic fairness component to this that I haven't worked in, but I think it's important. And it's also sexy if you like to publish, like people like that stuff. So this is just showing you that like there's work to do. Like this isn't great. So here's how I want to fix it. And I'm going to give you the kind of, like I didn't solve this problem. So like there's positive results and negative results, but here's the new idea. So what we're going to do is we're going to create, so remember, if we were doing linear regression, but think of it in general, this would be the whole space of parameters. These are my B's, and I got to find the parameters that have minimized the loss function, right? So I'm going to create a probability density over the whole space of models, right? All the betas. So this, you can think of it as like a blanket curving, right? And I'm going to make it so that the high probability parameters are the ones that are really near optimal. They give you really good machine learning algorithm. And the really low probability ones that are like in the tails of this distribution, they give you really bad accuracy. And now if I can just sample from this, I'm probably going to get something really close to optimal, right? Because I'm going to get high probability stuff, or at least close to the mode. And I want to create this so that I get strong differential privacy. That's the idea. So this has already been created. This guy at Harvard created this mechanism. It's called the exponential mechanism. And it's so stupid, easy, that it's not as clever as I just made it sound. Your utility function is negative the loss function, right? Because we want to minimize loss, so we're just going to put a negative in front of it, and then we want to make that big. Do e to that. Where is that really big? Where your loss function is where you want it to be. And where is it really small? Everywhere you don't want it to be. And then divide by whatever constant makes that a distribution. So that's what this C1 is. in order for it to satisfy differential privacy, I got to put a 2S there. S is the sensitivity of your loss, and I'll show you that's a problem that we can deal with. If you can sample from that, you can mathematically prove that you'll get near optimal parameters, and he proved it in the 2007 paper. And here's the real world problem. We can't sample from it. We have no way of sampling from this distribution. So this is a density learning problem now. So there's two problems, and I mentioned them. We have to compute that S, which is generally hard, and we have to sample from this. So who knows what a normalizing flow is? Oh, great. These are like, yeah, you got them? Yeah. These are like, if you like math and you like machine learning, I think these are just like candy. We're going to go back to your calc. By the way, how am I doing on time? I'm fine. I have like 15 minutes, 12 minutes, something like that. We're going to go back to your calculus class. And remember when you learned how to compute this integral? How do you do it? You do u substitution. So you go, oh, I'll let u be x squared. I got to compute du dx, so I'll know that du is 2x dx. And then when you do that substitution, you get this out, right? Forget that mechanism for a minute. Just observe something. This integral is 1, and this integrand is always positive, so that's a probability density. You know that 1 equals this, and because the u substitution equals that. So this integrand is a probability density, right? Okay, I just showed you how to take one probability density and turn it into a harder one. Just make a change of variables. Then you just substitute with a change of variables, and you have to put in the derivative to make sure it integrates to 1. So there's a theorem. It's called the change of variables theorem. Suppose that I'm switching variables. Instead of x and u, I'm doing z and theta. You have a change of variables. So what do I mean by change of variables here? I just mean it's invertible, like it's a bijective map. And you can do the derivative both ways. You can do the derivative of f, you can do the derivative of f inverse. Then, if you have this guy pz, this is the guy you start with, I can make a new distribution p theta. How do you do it? Well, z is just f inverse theta, so that's why I needed invertibility. That's like the u and the x switch. And this is where you did the du dx thing, where you multiply by the derivative. When you're in higher dimensions, the derivative is a Jacobian matrix. What's the area of the unit square when you apply a matrix? It's the determinant. And you're doing, area calculations when you do integration. That's why you need the determinant. If you flip orientation, you'll get a negative, so we just do an absolute value because we want area or volume. So the point here is it's literally the exact same thing you did when you change variables in like your first integration class. Gives you a way to map probability densities to each other with any change of variables you want. So all we're going to do is create a deep learning neural network where every single layer is a change of variables. And then we can start with a probability density that we know, like the normal distribution, because we can do everything with that. And we know the output is also a probability density if we just multiply by the derivative of that. It's actually the inverse derivative of that neural network. So this gives us a way to start with a probability density and use the really expressive power of neural networks to curve and morph it into some really hard density. And my idea is maybe we can do this to sample from that exponential mechanism. Remember, the big problem here is we can't sample from that guy, but it's a really clever solution. So that's the research that I'm going to show you. Here's what these look like. So I'm going to start with the normal density. F1 is a change of variables. It's invertible and differential, but it's also a neural network layer. So you multiply by a matrix, then you apply a nonlinear function to each component. That's all it is. Do that a whole bunch of times. On this end is this hard density that I cannot sample from. I can compute it up to a constant. Remember, it's just e to the loss function. You can compute your loss function. You can take e of that. So I can compute it up to a constant. That's all I need to do to train this network. What you do is you take this, think of it like this. You take a normal density and you take your untrained network, and that normal density gets curved and shifted into something. I want that something to be this guy, so I take the KL divergence between them. The KL divergence is a way to measure how far two probability densities are from each other. That's our loss function. If that's 0, they're exactly the same density. And then I just minimize that. And that tells me what parameters to put in that model. So it curves and shifts our normal density into the hard one. And here's some pictures where they started with a normal density and they just colored it stripes. So you could see how it morphs things. they wanted a cross-shape density, and you can see how it did it. So these are really expressive, and they're pretty exciting. That's from a paper. Boy, you can't see that. We sampled from this, and you can see the samples match that, and you get some down here. It's from a paper, and we created it to make sure our code works. The hard part of doing this, I'm going to go back. You have to compute the Jacobian of the inverse of this neural network. You have to be able to compute that. So, well, we get to design the neural network. So you design the neural network so it's both expressive, but you can compute that. And so we use what are called Sylvester flows, and it exploits this linear algebra theorem. If you take that guy, you know that its Jacobian is the identity plus A times B, where A times B are the matrices in that form. And here's the trick. These aren't square matrices. You make them long and skinny. And the determinant, you can do it in the skinny space or in the long space, and you can choose whichever one's computationally better. So that's how we got around that. So let's step back for a minute. The way I told you we train machine learning models, forget privacy, just think about training a machine learning model. The way we do it is we take our loss function, we compute a gradient, we step in the opposite direction, we do that over and over until we converge. I just gave you a completely different way to train a machine learning model. You make this ridiculous density where the really good parameters are the really high probability. And then I just gave you an auxiliary neural network you train that allows you to sample from that. And I'm claiming that we can train a model this way. The first question is, can you train a model? Right? And I'm going to show you that you can. I guess I should step back. I didn't say one thing. When you train this guy, what I really want is a sample from that one. After it's trained, you sample from your normal, which your computer can do because of the central limit theorem. It's like the math gods are very happy and they gave us this amazing tool. We can sample from normals really accurately. And then you just push it through the trained model, and it's provably a sample from the hard one. So that's how we do it after you train it. You just sample one time and push it through. So it's really fast once it's trained. This is a picture of the whole thing. So here's our private data set. We're the bad guys, right? We're the outsiders that can't see the data. We want to train this machine learning model. We have to give them a loss function. They make negative loss function. That's the utility function for the exponential mechanism. Here's the wonky density. There's the normal density. We have to train this auxiliary normalizing flow network. Once we do, we sample from that, push it through, and we get the parameters, which I called theta. Instead of, I used B's on the original slide. That's what you would give to the world. That's the trained neural network. So the hope is, one, this guy is accurate. It's approximately optimal. And the second hope is that we can prove differential privacy for it. And that's our conjecture. We're going to move that curve that I showed you out. How do you actually do this? So there's the format of the density we got to sample from. The U is negative loss. Write down a loss function. They're almost always of this form. So X is our data set. Theta are the parameters we want to learn. Basically every data point there, so that's like an xi, yi. Actually, that one xi is representing both. There's a how far is that from the real answer for the thetas I have. So this little l is the loss of each one data point. And then usually you have a regularization term. If you're not familiar with machine learning, that keeps your parameters from getting really big and wonky directions and overfitting. The first thing we have to do is come up with that S parameter, bounding sensitivity. So what is it? It's the max across any two training data sets, not just ours, but any true that differ by 1 point of the loss. When you write that down, all of the terms here cancel except for the one data point you changed. So, and the regularization term cancels because there's no X's there. So that's really nice. And you just get the difference of the loss on the one data point you changed. So this little loss function, you just have to either bound its L infinity norm or show that it's Lipschitz, and you're done. If you assume you're doing binary classification, your outputs are bounded between 0 and 1. So you get a bound because it's L infinity. Everything's bounded by 0 and 1. And the bound is 1. It's like really easy to prove. So we just restricted ourselves to that case for now. But in general, if you're doing regression, if you can put bounds on how big the outputs could be, you'll get a sensitivity bound. That's for L2 loss. If you move to like binary cross entropy loss, which is super common, it's much harder, and we can talk about that. But we have it for L2 loss, and it works great. So we'll just use that. So there's your sensitivity bound in the theorem. So then we did it. We went and trained those flows that I showed you with the A and B matrices. They're called Sylvester flows. This is the healthcare data that I showed you those results on. So this is electronic healthcare records. This one is not the mortality benchmarks. It's predicting how long you're going to stay. It's binary on whether you would be in the ICU for more than 3 days or less than 3 days. The reason they chose that cutoff for the benchmark is it's 50-50. It's a balanced. The mortality benchmark is imbalanced. Most people don't die in the ICU, so that's why we did both. These green dots and diamonds are the state-of-the-art implementation of differentially private stochastic gradient descent. That ships with PyTorch. We did a ton of hyperparameter searching. We are constrained to use L2 loss because of that sensitivity bound. They are not, right? You can apply them to anything. So we did it with both because they should use the best. In the real world, you would use whatever's best. And you can see that curve I told you about. This is epsilon. So here I'm starting at 0.5 and going to 10. And you can see it's starting to drop off pretty hard at 1. This is showing like what happens if you really try to push your privacy to be better by orders of magnitude. And you can see accuracy-wise, we can train models with these epsilon parameters, and the accuracy is awesome. The dotted line is what happens if you don't care about privacy, if you just train a model in the real world. So this is really positive. The one thing we showed here is that you can train a model with our method, and you can do it with really aggressive epsilon parameters. I am not claiming epsilon differential privacy for our method. And I'm going to show you why in like 2 more slides. The next question is, can you compute this? Like, how computationally expensive is it to train with our method versus training with, differentially private stochastic gradient descent? And my partner on this project, Vandy Toombs, thanks to her, we are faster than PyTorch's differentially private stochastic gradient descent. And the way she did this, she's like a really clever programmer. You have to basically instantiate, to train that normalizing flow model, you have to instantiate like 1,000 of them at once. And she built a PyTorch class that basically, instead of having an array of parameters for one model, it's a 3-dimensional array, like a batch of parameters. And it does all 1,000 at once. And the reason why is PyTorch can use GPUs to do all those computations quickly. So by making it one model, she tricked the GPUs into doing it, and we won. So you can, if you're a clever engineer, which she is, and by the way, she's a mathematician. The fact that she can program that well is I don't understand how she got both. But yeah, so we proved that you can do this faster than the current state of the art. Last problem, this is the negative results. This is what we can't figure out. I want you guys to solve this problem and publish it, and we can advance the whole state of the art for the world, because I haven't been able to get it. We're supposed to sample from the real exponential mechanism. Remember, I'm using a normalizing flow to approximate it. It may not be exactly the right thing. And these are not real data. I just drew 2 curves to show you, like, we're supposed to sample from purple, but we're actually sampling from green. You can write down what that means. We know this is true. This is the definition of differential privacy for the exponential mechanism. So I'm using P to be the density that we're supposed to sample from. And X and Y are the 2 data sets that differ by 1 data point on this slide. We're approximating it, and I'm using Q to denote our approximation. So we know that. We have to prove this, and I don't know how to prove it, is what I'm saying. Here's a real picture from real data. I wanted to see what was going on. So I took a logistic regression model that has 2 parameters, and the reason I did 2 is because I could plot it in 3 dimensions. This is the real density. So the way remember I can compute it up to a constant for every point. I just sampled a ton of points, computed it, and then divided by the constant that would make it sum to 1. And this is what the normalizing flow outputs. So let's think about this. Clearly not the right distribution. It's too precise, and that's actually a technical term. When a density is too precise, it means it puts too much of its mass at the mode and not enough at the tails. So this explains our previous results. Remember, our results here are that, like, we're so much more accurate than they are, even when epsilon's really small. Well, when epsilon's really small, the variance isn't big enough to give you that privacy. The variance is small, so you get really high accuracy, but likely we don't have good enough privacy. That's my intuition. I can't prove that. So we're going to do some empirical methods to see if it's private at all. So remember at the beginning of the talk, I said, if we release a machine learning model trained with no privacy, you can figure out who is in the data set. I'm going to tell you how that attack works. So this is the state of the art. That's called membership inference. If you have a model and you have a data point and you say, I want to know if this data point was in the training data set, this is how you do it. So the first thing you do is you go get a whole bunch of data, and you take like all that data and you train a model on it. and you set it aside. And then you take the same data and you add the data point that you want to know if it was in the real data set, and you put it in the data set and you train a model on it. So now you have two shadow models trained on whatever public data you could get. One has the data point you care about in it and one doesn't. Do that 1,000 times or 10,000 times. And now take your data point you care about and put it into the trained models, put it into all of them. And you're going to get an output that's, say, between 0 and 1 if you're doing binary classification and it gives you a confidence of 0 and 1, and plot those. You're going to get a distribution. That's the distribution of outputs of a model that was trained without your data point. Now go to the 1,000 models that were trained on data sets with that one data point in. Do the same thing. Plot the outputs. You're going to get a histogram, right? That's the approximate density of if you're trained in there. If those are right on top of each other, you can't tell. If they're far apart, you can tell. Now go to the public model that was trained on the private data, and you don't know if that data point was in there. Take the one data point you care about, look at the output, see if it's more likely from one histogram or the other, and that tells you. You just take the definition of differential privacy and you flip it on its head. So Carlini, who I actually met 2 days ago at Alan Turing Institute, which was quite the honor, that's the state-of-the-art membership inference attack, and he came up with it, and I got to see him give a talk. So we did it for ours. Those are the two histograms I described. We trained 1,000 shadow models, one with the data point we care about in it, one without. We applied some post-processing to make them normal. So a logistic, these are QQ plots. They look at the p-values of the empirical density versus an actual normal. If it lies on y equals x, you're normal. So that's a check you should do if you're going to use approximate normals to make sure you're not assuming anything. And then we create a threshold where we say, you know, if it looks more like one than the other, like how big of that threshold do we say, oh, it was in the data set versus not? So we turn the continuous output into a binary. And then we can do an ROC curve. So this is our false positive rate. This is our true positive rate on being able to guess whether a given data point was in the training data set or not with this method. And as you move that threshold parameter, right, you can change your false positive versus true positive. We did a log-log plot. The reason why is when you do membership inference attacks, you want very low false positives. Like if you're going to put a lot of resources into trying to use someone else's credit card because you somehow stole it, you don't want to be wrong. You don't have to know everyone's. You only need to know one credit card. You just have to know 100% that it's in there. That's why you zoom in on the low false positive rate. If you land on y equals x, it's random guessing. The blue line is if you had no privacy. See how it's higher? You can get more true positives with a no false positive rate. It's easier to attack than R2. That's good. That means the privacy is working. The green is differentially private stochastic gradient descent. That's the state of the art. It's lower than ours, which means it's harder to attack, so it's more private, and ours is in between. So we did this for all those different epsilons I showed you, for logistic regression, which is like the easiest model in the world, for the GRUD model, which is a really difficult recurrent neural network made for healthcare data. And the result, and we did it for two different benchmarks of real healthcare data. The results are on the logistic regression. It looks like this. The empirical results are we get privacy with our method, but not as much as DPSGD. With the deep learning model, you don't need privacy is basically what it gets. They all lie, all three of these curves lie on y equals x, so it's indeterminate. Like we can't conclude anything. So I think we get privacy. I think it's worse than differentially private stochastic gradient descent. Like we're not getting what the epsilon says, and I just can't seem to prove it.